Good morning to everyone.
Good morning.
So today, Professor Sugny is going to present understanding the quantum world with the tennis racket, how classical mechanics help control qubits. It's our pleasure. The stage is yours.
Okay, so thank you very much, Dardan. So thank you also to the organizer for the kind invitation. And today, I'm going to talk about classical effect, the tennis racket effect, and I'm going to show you how we can use this classical effect in order to control, for instance, qubits. So this work is a joint work between mathematicians, physicists, and chemists. And so I would like to mention my co-workers, the group of Stefan Glaser in Munich and the group of Pavel Mardezik in Dijon, so a group of mathematicians. And I would like also to thank my different fundings, and in France and in Germany, but also the QuSCo European project. A short introduction about quantum control, just to give you a very rough idea about the state of the art. We have nowadays a very good theoretical basis to explain the nature and the behavior of matter at the atomic or microscopic level. And one current idea is by now to try to use such understanding of fundamental quantum effects to create and to develop some new technologies that we call, based on quantum effects, that we call quantum technologies. And one very efficient tool to realize such technologies or such task is control theory. So that's why control theory will be, I think, in my opinion, one of the basic tools to transform such, in the near future, to transform such quantum effects into quantum technologies. And I give you here, with this picture, a short example of a realization of a basic operation. So I consider here a Rubik's Cube, and the goal is to go from a random Rubik's Cube to a regular one, for instance, in minimum time or with a minimum of energy or with a minimum of manipulations. And so we can use control theory to compute, for instance, the minimum number of manipulations we need to transform this random Rubik's Cube into a regular one. For quantum control, for sure, the goal is to manipulate the quantum dynamics of atoms, molecules, or spins by using some specific time-dependent external electromagnetic fields. So to realize some specific task, we need to design, this is electric or magnetic fields, and to compute the time-dependent evolution of the fields. So we can use the tools of control theory. So we have a very general mathematical framework. So in control theory, in applied mathematics, for instance, this framework, this mathematical framework can be used in many different areas. So for instance, in classical physics, and one of the first example of application of optimal control theory was the control of spacecraft in space dynamics, with the examples of the Apollo missions and the Smart 1 mission. So the Smart 1 mission, the goal of the Smart 1 mission was to take a picture, for instance, of a dark side of the moon. And so the goal of control theory and optimal control theory, where we try to optimize some quantities. So during the time evolution, was used. Optimal control theory, for instance, in such examples, was used to compute the best trajectories. For so for the different spacecraft. And so we can apply this very general mathematical framework also in quantum physics. So there are by now many different examples. And in general, so due to the complexity of quantum dynamics, so we have to use some numerical optimization algorithms. And so finally, we get a numerical solution or a numerical control field. And one question that we can ask as a physicist, because it's also very important for a physicist to know the time evolution of a control field, but also to have a physical understanding about the control mechanisms, is how we can build up a physical intuition about the quantum control, or about the mechanisms we use during the control process. And so today I will try to show you on one specific example that, so for that purpose, we can use the analogy with classical physics. So by using classical physics, so we can build up this intuition, and so we can understand the mechanisms that, so at least for one example, quantum control uses. Okay, so it was a very general introduction, and now I'm going to enter into the details about the classical effect. So I'm going to describe today and to study the tennis racket effect. So it's a very well-known geometric phenomenon or geometric effect that we can observe in the free rotation of a classical rigid body. And it can be observed in any three-dimensional asymmetric rigid body. So with this picture, so we have a global view about the experiment. So in general, so I'm not going to use my racket, but I have a racket, and so I can make the experiment during the conference. So here we have only a picture and a short video in the next slide. But so the idea is the following. So we have a tennis racket, so a very standard tennis racket. And so the first point is that we need to distinguish the two faces of a racket. So for instance, here we have a white one and a red one. So we assume at the beginning that, so we take the tennis racket by the handle, and we assume that at the beginning of a motion, for instance, that so the white face is facing up. Okay, so the goal is then to throw in the air so the tennis racket such that so the handle makes a 2π rotation, so a full rotation around the transverse axis, so which is this axis. So this axis is belongs to the head of a racket and is orthogonal to the handle. Okay, and during this full rotation of the handle, so we observe at the same time a twist of the head of a racket. So in other words, it means that so after this full rotation, that when you catch here, so at the end of a motion, you catch the tennis racket, that so it's finally so the red face which is facing up. Okay, so we have a twist of pi of so the head of a racket. So you start with a white face, and we arrive at the end of a motion, so with the red face. Okay, and it's basically so the essence of the tennis racket effect. So now just a short movie, and you can try, so this evening, so if you have a tennis racket at home, so try to make so this motion, and you will see that most of the time, so for most of so the initial conditions, you will observe so this effect. So it's a very robust classical effect. So here I have so a short video. So in order to explain you so this effect. So we start here with a blue face, which is so facing up, and at the end of the motion, it's so the red face. Another very interesting geometric effect, which is connected to the tennis racket effect, is so that we call the monster flip. So the monster flip is a freestyle skateboard trick. Again, so the idea is to make a full rotation of the skateboard around so the transverse axis. So it's so this axis, which is in the plane of a board and orthogonal to the longitudinal axis of a board. But so this time, so for sure, so the goal of a monster flip is to try to avoid so the tennis racket effect, such that so the wheels, so after so the full rotation, so fall back to the ground. While so if we use the tennis racket effect, so the wheels should end up in the air. So I'm going to show you so this short video, so showing illustrating so the monster flip effect. So we have a full rotation, and then so the wheels so fall back to the ground. And so we can find some movies on the web. So a real skateboarder with a real, so in the real life, with a real skateboard, and it can be shown that it's possible. So even if it's not in agreement with the tennis racket effect, so it's possible, but only with a very low probability. So in other words, it means that we need a very specific position and a very specific speed, so for the skateboard, in order to realize so this monster flip effect, and in order to avoid so the tennis racket effect. And okay, so my goal, so in my talk, will be so during the first part to try to explain so both so the tennis racket effect and so the monster flip effect, to describe so from a mathematical point of view such effects. And so there are so such effects are so very well known. So we can find so Wikipedia page, so many movies about such effect. But finally, so there are very few rigorous or mathematical papers about such geometric phenomena. And so that's why, so 3 years or 4 years ago now, so we decide, so with so my colleagues, so to publish 2 papers, so one in Physica D and another, so last year in Physical Review later, to explain so the physical and the mathematical origin of so this effect. So we have also published, so I'm sorry, so in French, 2 popular papers, so one in Images des Mathématiques, which is a journal from the CNRS in France, and one in Le Monde, so with a journalist, so David Larosserie. And you can find also a course, so a popular course from physics girls about so the monster flip and so the tennis racket effect. And this effect, so I would like also to mention this point, is known also as the Dzhanibekov effect. So Dzhanibekov is a Russian cosmonaut who made a similar experiment in 1985, so in a spacecraft in zero gravity with a wing nut. So it was the first real experiment, so without, so with zero gravity. Because otherwise, so when you throw in the air your tennis racket, so if you want to describe so with accuracy so the motion, so you have to take into account the gravity. Okay, and okay, so now to explain the tennis racket effect, so I have to go back to the basics of classical mechanics and to the rotation of a three-dimensional rigid body. So it's something which is very well known, and you can find so this information in many textbooks, and in particular in the textbooks by Arnold about classical mechanics. So the point is that so the position, so in space, so the rotation of a rigid body is given by an element of SO3, so a rotation matrix, and this rotation matrix describes so basically, so the rotation of one frame with respect to another frame. And so we have a fixed frame, so the space fixed frame. So in my, so here picture is capital X, it corresponds to the axis capital X, capital Y, capital Z. And so we have another frame which describe basically, so the position in space of a body fixed frame, small x, small y, and small z. Okay, and so with this rotation matrix, so I can describe so the position, so basically the position of a body fixed frame with respect to the space fixed frame. And so in general, we use three Euler angles as coordinates to parameterize so this rotation matrix. So here, so this choice is not unique, and here, so we consider so the angle, so theta, phi, and psi, because so this choice is well suited to the description of the tennis racket effect. So the next step is to discuss about the mass repartition of a rigid body. So in general, we introduce so the inertia matrix. So it's a symmetric 3x3 matrix. So we can compute so the eigenvectors and eigenvalues of so this matrix. So the eigenvectors lead to the inertia axis. So here I give you two examples, so for a skateboard and for a tennis racket effect. And so, okay, so X, Y, and Z, which are given so from so the inertia matrix, and so we have also some eigenvalues, which are called so the inertia moments. So we have three distinct inertia moments that we call EX, so IX, IY, and IZ, and they correspond to the different so inertia axis. And so we will use so in this talk so the following convention, and for an asymmetric rigid body, so the three inertia moments are different from each other. Okay, and we see, so it's another interesting point, that finally, so both for the tennis racket effect and for the monster flip effect, so the goal is to make a full rotation around so the transverse axis, so the y-axis here and here, which correspond so finally to the inertia moment, so in the middle. Okay, so not the lower or the upper, the lowest or the uppest so inertia moments, but so the intermediate one. Okay, so it's a second information that we use to describe so the rotation of a rigid body. And another idea that we use is the fact that so we can use a reduced phase space to describe so this motion, and this reduced phase space is given by so mx, my, and mz, so the coordinates of the angular momentum in the body fixed frame. Okay, so it's so with this reduced phase space, we don't have so all the information about the dynamics, but it gives a part of this information. And the interesting point is the fact that in this space, so we have two constants of a motion. So the energy of rotational dynamics, which is given of the coordinate. As a form of a coordinate and so over two constants of a motion define finally so two surfaces in this three-dimensional space, and the trajectory is so the intersection of the two surfaces. So here is a specific picture. So for some specific values of the energy E and so the angular momentum M. And so here in light gray, so we have so the sphere, so corresponding to so the norm of the angular momentum. And in dark gray, so here we have so the ellipsoid corresponding to this constant of motion to the energy. And so finally is so the intersection of this sphere and this ellipsoid, which gives you in the reduced phase space so the trajectory, or here two distinct trajectories of so the rigid body. So here so we have the trajectory which correspond here to this intersection and to this line. Okay, and in general, to have a very simple picture, we plot, so we fix so the norm of the angular momentum, so for instance to 1, and so we vary so the energy E, and for each energy E, so we have some trajectories, so a given intersection, and then we plot on the same sphere all the possible trajectories. So it's that we did here in blue and in red. So we have different trajectories corresponding to that we call the rotating trajectories and the oscillating one. And at the border between the two families of trajectories, so we have so that we call the separatrix. So it corresponds here to the dashed line. So we also have in this reduced phase space different equilibrium points, which correspond either to the rotation around the x-axis, so for this point and so the opposite one, to the rotation along the z-axis, so for this point and this one, and to a rotation around the y-axis. And the interesting point is the fact that, so from a classical point of view, so we have 4 stable points, so this one, and the 2 others, and 2 unstable points associated with so the equilibrium points along the y direction. And in particular, so we see that so the separatrix connects so the equilibrium point in plus y and the one in minus y. Okay, so we will use so this information so to describe the tennis racket effect. And now so I can really come back so to the description of this effect. And so I just recall you so the definition of so the Euler angles so we choose so to describe so the rotation of the rigid body. And so here in this picture, so I also plot so the position of a tennis racket, and so we see, for instance, that the theta angle describe so with respect to the capital Z axis, so the position of the handle of a racket. And so for a tennis racket effect, so with this choice of Euler angles, so we have so the following relation. So theta, so we can show that theta is of the order of pi over 2, is almost constant along so the tennis racket effect so trajectory. So it means in this picture that so the handle here is in the equatorial plane, so in the capital X, capital Y plane, okay? And then, so we induce a full rotation of the handle, so it just means that, so here, the small z axis, so makes a full rotation, a 2 pi rotation in this plane. So at the end, so delta phi will be equal to 2 pi. So delta phi, so finally measures so the full rotation of so the handle. And during this full rotation, so we have also a twist of the head of the racket, and this twist is given by a variation of psi, and this variation is of the order of pi. Okay, and so we have so pi if we have a perfect tennis racket effect, and otherwise, so we have something which is of the order of pi. Okay, so now, so I have to enter so into the details of the differential systems to describe even more so the tennis racket effect. So for that, I have to introduce so the Euler equations, which give the dynamics of the angular momentum in the frame attached to the racket. So basically, so the Euler equations are written so there. So it's just a system of nonlinear differential equations, which couple so the coordinates mx, my, and mz of the angular momentum, and we see that here so we have as coefficients so the different moments of inertia. Okay, and we can also, so here is so the dynamics, the system of equations describing the dynamics of the angular momentum, but we can also find so the dynamics of the Euler angles. So basically the first step is to express so the coordinates of the angular momentum as a function of the Euler angle. So it works for theta and psi. So then just by computing the time derivative of mx, for instance, and my and mz, so it's straightforward to get so the time derivative of theta and psi. And so for phi, so it's a bit more complicated, but so we have just to come back to the connection between so this angle and the angular velocity to establish so this equation. But you can so find so this kind of equation in any so standard textbooks of classical mechanics. Okay, and so in the next slides, I'm not going to use so the coefficients Ix, Iy, and Iz, but so the following coefficients, so A, B, and C. So A and B, so the coefficients A and B describe so the asymmetry of a rigid body, so basically the shape of a rigid body, and in the limit where AB, so the product AB goes to plus infinity, so we are in the limit of a perfect asymmetric rigid body. Okay, so that's why so it's something which is quite trivial. So it's just a change of variables, and we also introduce so the parameter C, and so C is connected is related to the energy. And so, for instance, C is basically the distance to the separatrix. So if C is equal to 0, then it means that we consider a trajectory along so the separatrix. Okay, so now I think so we have all the material to describe so the tennis racket effect. And another so very interesting point, so from a qualitative point of view, is to make the following comment. Is the fact that the tennis racket effect is a geometric effect which does not depend on the duration of the process. So finally, so the goal is to observe so this twist, but so it's not very important that this twist occurs in 1 second, in 5 seconds. So the time evolution of the different observables is not crucial to describe the tennis racket effect. So that's why we can reduce the dynamics, and we can consider only 2 angles, psi and phi, and so we can introduce a kind of momentum that I call psi dot. And psi dot is just the derivative of the angle psi with respect to phi. Okay, so by playing with the different equations, so it's with some simple algebra, we can arrive at this kind of equation where this momentum can be expressed as a function of psi and as a function of the 3 parameters, so A and B, which describe the shape, basically of a rigid body, and C, which correspond to the distance to a separatrix. And so what is the interest of this change of coordinates is the fact that now I have a new reduced phase space in terms of the momentum as a function of psi, and in this diagram, the angle phi plays the role of time. Okay, and here we have something which is very simple, and so we recover something which is very similar to the phase space of a 2-dimensional planar pendulum. So indeed, in blue we recover here the oscillating trajectories. In black, here we have the rotating trajectories, the same as before, and in red, the red curves correspond to the separatrix. And here again, we have the 2 unstable points, one here and the other here, which are connected by the separatrix. Okay, and so we can use this analogy with a planar pendulum. So here I recall you the standard phase space of a planar pendulum. So we have a parallel that can be made between the 2 phase spaces. So the only difference is basically the distance here between the 2 unstable points, between this point, and between this one and this one. So in a standard planar pendulum, basically we have a variation of 2 pi between the 2 unstable points, while this variation is equal to pi for the rigid body and for the rotation of the rigid body. And so this variation of pi is not a detail at all, and so this variation of pi is at the origin, finally, of the tennis racket effect. So this very small difference between a planar pendulum and a rigid body, finally explains qualitatively the tennis racket effect. So now we can make some numerical simulations to have a very general and global idea of this, in particular of the robustness of this effect. And so this picture summarizes this description. So here, I plot in this phase space. So for each initial condition, given by psi 0 and this derivative, I plot the twist that we can observe. And we see that for a large set of initial conditions around the separatrix, we observe a twist of the order of pi. So here we can consider any initial conditions as a function of psi 0 and the corresponding speed, and we observe a twist which is of the order of pi. So except in a very thin area, in very thin region here, near the separatrix, where delta psi will be of the order of 0, and this very thin region corresponds to the monster flip effect. So it means that when you try to make the monster flip effect with your skateboard, you have to choose, which is not so easy because you are on your skateboard. You have to choose a specific position. So it means a specific position. So for the board of a skateboard, and a specific speed to be in this very small region. Okay, so this kind of numerical simulations explain why the monster flip effect is a very difficult skateboard trick, and it's very difficult to realize. I'm not going to enter into the details, but so in our last PRL paper, so we give a complete and rigorous mathematical description of the tennis racket effect. So the idea is, so we know that so the trajectories can be written in terms of elliptic integrals. So to be more precise, in terms of incomplete elliptic integrals, and the goal is to work on such integrals to explain and to quantify the tennis racket effect. So in particular, so we have shown that we can express the variation delta phi as a function of this kind of elliptic integrals where x is connected to the cosine of psi. So we make this change of coordinate, and by studying this elliptic integral, so we introduce a complex phase space, which is in mathematics a Riemann surface. So we can understand the behavior of this integral in terms of the singularity of the surface. So here I'm not going to discuss this point, but finally, so it's a beautiful mathematical and geometric result. So I think so we can explain this classical phenomenon in terms of a singularity of a complex phase space, in terms of a singularity of a Riemann surface. So in particular, so this singularity corresponds here to a pole which appears when C goes to 0. And by using the Picard-Lefschetz formula, which is a very well-known formula in complex geometry, so we arrive to the following expression, which is exact. So for delta phi, which can be written as a function of a bounded function. So epsilon is just here a parameter which describes the defect to a perfect tennis racket effect. So epsilon is equal to 0 if the twist is equal to pi. And we have also logarithmic divergence of delta phi. So we have mathematical theorem describing the tennis racket effect. But maybe for physical applications, so it's more interesting to focus on this expression. And with this expression, I give, with a very good accuracy, the defect epsilon to a perfect tennis racket effect as a function of A and B. Okay, so A and B describe, I recall you that A and B are two parameters which describe the shape of a body, and delta phi. So for delta phi equal to 2 pi, so here we have just pi, and we see that when we have an asymmetric, a very asymmetric rigid body, so when the product AB goes to plus infinity, then this term goes to 0, and we observe a perfect tennis racket effect. And we can show that this approximate formula works very well, and can reproduce with a very good accuracy the numerical results that we obtain. So if we integrate so the differential system. Okay, so we can make exactly the same analysis for the monster flip effect, where we get so the following approximate so formula. So here, so the difference is the fact that here we have a plus instead of a minus in the argument of the exponential, and it means that when AB goes to plus infinity, so we need to have a parameter beta, which corresponds basically to a C, which is proportional to the parameter C, so very small, in order to have a very small parameter epsilon. And a very small parameter epsilon means, so for the monster flip, a perfect monster flip effect. So it means, so if you have a very asymmetric rigid body, so a skateboard, so you need to find or to choose a trajectory which is very close to the separatrix in order to realize so the monster flip effect. Okay, and so this formula so concludes so this classical part, and now so the next question is to try to apply such classical results, so describing so this is geometric phenomena in the quantum world. And the idea is so the following. So we are going to use a formal equivalence between the Euler equations and the Bloch equations. So here on the left, so I write so the Euler equation that we use so for the moment, and here on the right is the Bloch equations, which describe, so for instance, spin 1/2 particle in magnetic resonance, but also the dynamics of a two-level quantum systems. So here M, so the vector M corresponds to the coordinates of the angular momentum, and here M is so the state of the system, so it corresponds either to the magnetization vector in magnetic resonance or to the coordinates of a density matrix if we have a two-level quantum system. And so we see, so it's a very naive and trivial comment that if we identify so omega x, omega y, and omega z, which correspond for a spin 1/2 particle to some external control fields, if we identify such control fields to so the coordinates of a momentum divided by so the moments of inertia, then so the rigid body and the spin 1/2 particle will have exactly so the same. So from a mathematical point of view, will have exactly the same trajectory. Okay, and so it's so we propose to use so the tennis racket effect so in the quantum world, so to control so the qubits by using so this equivalence. And for sure, so the moments of inertia so do not mean so anything so in quantum physics. And here, so we will use the moments of inertia as three parameters in the control of a qubit. So I'm going to discuss so this point in the next slide. Okay, so we have so this formal equivalence. So I just change so the labels, but it's exactly the same equations with the Euler equation and the Bloch equations. And about the identification, so we have one problem is the fact that in general we have only two control fields available. So for instance, along two perpendicular directions, and not three. So we cannot identify directly so the control fields to the coordinates of the angular momentum, but so we can use so this idea. So if one of the moments of inertia goes to plus infinity, then finally the corresponding term goes to 0, and so we can still use so this identification. Okay, and there are different choices according to the experimental setup. So we consider the case A or B. So it just depends on the direction of the two control fields, on the two control parameters that we use to manipulate the qubit. Okay, but so it works, and we can also show even if one of the moments of inertia goes to plus infinity, that so basically all the results that we have about the tennis racket effect and the monster flip are still so valid. Okay, so up to some small corrections. So basically we can use exactly the same formalism. Okay, and so now I can describe in detail so the different control strategies. For instance, in the case A, so without loss of generality, since the moments of inertia are some free parameters, I can set so I1 equal to 1 and I3 equal to 1 over k square. So k is just a free parameter, so finally belonging to the interval 0, 1. And so the first interesting point is the fact that in two limits, when k goes to 0 and k goes to 1, we recover some standard solutions for qubit control. So in particular, we can show that when k goes to 0, we recover the pi pulse, so a resonant excitation of a qubit or of a spin 1/2 particle. And when k goes to 1, we recover a very standard adiabatic pulse, which is known in the literature as the Allen-Eberle solutions. So here I give you so the mathematical expression of the corresponding two control fields. So in terms of hyperbolic functions. But so the interesting point is that so we have a very interesting family of control pulses with as a limit so the resonant pulse and so in the other limit the adiabatic pulse. But finally, if you change so the values of k, so we can go so in a continuous way, so from a pi pulse to the adiabatic pulse, and in particular with this parameter k, so we can play with so the control time and with the robustness of so the pulses, and so we have a very interesting so family, so with some analytical expressions depending on this parameter k. So it's possible to realize and to make some experiments. So this experiment was done in so 4 years ago, so in the group of Stefan Glaser in Munich. So for the control of a spin 1/2 particle, which corresponds, so here we plot so the time evolution of the coordinates of the magnetization vector. And so for instance, so here, so in red, so we have the coordinate so M3. And basically, so when we go from 1 to -1, so we go for a two-level quantum system or for a qubit from the ground state to the excited state. With so the solid lines, so we have the numerical simulations, and the crosses correspond to the experimental points. So here we see the very good match between theory and experiment. So in this magnetic resonance experiment. And basically it's so at the quantum scale, so in the quantum world, it's the equivalent to throw in the air so your tennis racket effect. To throw in the air your tennis racket, sorry. So we can also verify so the robustness issue. So for instance, here we consider two standard robust parameters, so alpha, which correspond to the control field inhomogeneities, and delta to the inhomogeneities of the offset. So we have verify so on this plot, so for a specific value of k, so the robustness with respect to alpha, So it's here in blue. So for a spin 1/2 particle of this pulse, and the weight curve correspond to a standard pi pulse or to a standard resonant pulse. And so here we have some experimental results, and here is just a picture showing you so the evolution of the robustness as a function of k. So in the limit when k goes to 1, so basically we recover so the robustness of the adiabatic pulse, but just by changing so the value of k, so going from 0.2 to 0.9, so we can increase at will so the robustness, and so we can adjust so the robustness of the process we need in a specific experiment or in a specific device as a function of this parameter k. And so the additional interesting point is that so we have so the exact analytical expressions of the control fields and also of the trajectories in terms of elliptic integrals and Jacobi functions. So it's something which is very interesting to make so this connection between resonant or pi pulse and adiabatic solutions. And so we have so this the possibility to have so this continuous evolution between so the two solutions. Okay, and another point that we also show is so the implementation of qubit gate. So we can also use so by using so the tennis racket effect find some new control strategy in quantum computing. So to implement so one qubit gate. So here I'm going to give you the example of a quantum phase gate, so which is described by the following unitary evolution. But so we can generate so any one qubit gate. So basically. So I'm not going to enter into the details, but the idea is to use so here the Montgomery phase, which correspond for the tennis racket of a rigid body to so basically to the Berry phase so for a qubit. So basically with the Montgomery phase, so we can describe along a loop in the reduced phase space of the coordinates of the angular momentum. So we can describe the variation delta phi as a function of two terms, so a dynamical contribution and geometric one. So the dynamical contribution so basically depends on the time of the control process and on the energy, and the geometric one is only described so basically by the area delimited by so the closed loop that we consider in the space mx, my, and mz. And so the idea is the following. So in general, so the dynamical contribution is not robust with respect to experimental imperfections or experimental limitations, but so the geometric contribution is robust to some extent. And the idea is to consider the concatenation of two successive tennis racket effects in order to eliminate so the dynamical contribution. Okay, so I'm not so after some algebra, so we can show that it's possible. So the so here is one example where I consider so a closed loop. So in this space, where one trajectory corresponds to a tennis racket effect, and so the second one to another tennis racket effect. But so the two trajectories are described by different k parameters. So ka, so for the first trajectory, and kb for the second one. And so after some algebra, so we can show that delta phi and so the geometric contribution of the area of this of this region can be written so as follows as a function of Ka and Kb. Okay, and so we have to adjust so the parameter Ka and Kb in order to eliminate so the dynamical contribution. But if you do that, so finally, so here again, so we have a very robust process with some analytical expressions of the control fields in order to implement so here a quantum phase gate, because so here so the angle phi corresponds to this one, to implement so this quantum phase gate. Okay, so it's also something which is I think so very interesting so for quantum computing applications. So I'm not going to describe so this point, but another possible application of the tennis racket effect in the quantum world is to study the dynamics of asymmetric top molecules. So here I just give you so a rough idea. So with this picture where we consider the chlorobenzene molecule, where so this cycle here corresponds to the head of the racket, and so the chlorine atom correspond so here to the handle. And so we can find some signature of this classical effect on the spectrum of the asymmetric molecule and on the dynamics of the wave function. So in particular, so there is a very recent so PRL paper about so this effect, and it can be shown that so the tennis racket effect in the quantum world, so for an asymmetric, so for nanorotors or for an asymmetric top molecule, is persistent and very robust with respect to a thermal distribution of the initial conditions. And this point is due to the quantum tunneling that we can observe between the oscillating and the rotating trajectories of so the rigid body. But it's for the moment, it's just some numerical simulations, and one goal would be so to try to show so this effect on the from the experimental side, with, for instance, so the control in gaze phase of asymmetric top molecule by laser field. But for that, I think we will need optimal control, so to shape so the laser field, and in order to induce so the rotation of the molecule around so the transverse axis. So work is in progress on this point. And so I'm just going to now to finish so my talk with some perspectives. So we would like, and we are going to work on a lax pair approach of the tennis racket effect. So basically, so the idea is to extend so this geometric effect that we study for SO3 to SON. And so this is very interesting from a quantum point of view, because in this case, it means that we could apply so the tennis racket effect to an n-level quantum system, for instance. We would like also to have a rigorous semi-classical and quantum analysis of the tennis racket effect in the quantum regime. So to explain so the quantum tunneling and so the role of the quantum tunneling in the persistent tennis racket effect. And we are also interested in other physical or chemical applications of the tennis racket effect, and so we are working on experimental demonstration of a quantum effect. So basically for the rotation of asymmetric top molecules in gaze phase. So thank you very much. So maybe I'm just on time. Yes.
Thank you for your nice talk. Thanks for our invitation. Is there questions? So I have a general question. If possible, could you talk a little bit about the future perspectives and this direction?
So which direction? So I do not understand, and I cannot hear you. So which one?
For example, the lax pair approach.
Okay, yes, sure. So the idea of the Laxper approach. So the Laxper approach is a well-known mathematical approach to describe classical integrable systems with a very large number of degrees of freedom. So for instance, the Laxper approach is very well known to describe so many classical many-body physics. And so we can use this approach in particular to find the different constant of a motion to describe so the motion of a formal and abstract n-dimensional rigid body. And basically it corresponds to a description of a rotation matrix not in SO3 but in SON. And so we think that with this approach, so we can describe, so we can extend and generalize so the tennis racket effect to SON. And in this case, so we can use exactly the same mapping between SO3 and SU2 that we used so before. So the mapping between so the rigid body and a qubit. But this time between, for instance, so this n-dimensional rigid body and n-level quantum system, so with some specific couplings between the levels, in order to apply so this strategy and in order to design some new control processes so for n-level quantum system. And the interesting point is that since so the classical dynamics is integrable, so we expect that so the control field, so we expect to find some analytical expressions for the control fields. So it's a very good point, and so for the analysis and so for the understanding of the control mechanisms.
And
can you hear me?
And what's the control objective of the chlorobenzene?
So it's a good question. So for the moment, so for the chlorobenzene, so the idea is it's a fundamental question. Is just to be sure that so we can show from the experimental point of view that to verify that the tennis racket effect exists. So for this kind of asymmetric top molecule, so even if so we can make some numerical simulations, so it's just a challenge from the experimental point of view. So for the moment, is just to try to realize with some specific laser fields, so this kind of dynamics. And so it's a fundamental issue for the moment, but we don't have some specific control objectives, but maybe so we can find some applications because it seems so that this process, this dynamical process, is very robust with respect to variations of some parameters. So maybe we can find some other applications.
Okay.
I know Federico has a question.
Yes.
Hi everyone. Yeah, sorry for the call. Thanks Professor Sugny for the great talk. I just wanted to ask, what do the control fields look for the different Ks, and would there be any reason as to not to have a K reaching like approximately 1?
Okay, so it really depends on your experimental setup. So the main advantage of this family of pulses is that you can adjust so the parameter k as a function of your experimental setup, your device, for instance, as a function of the relaxation effects. Because when k goes to 0, so you reduce so the control time, because so you are very close to the resonant or to the time optimal solution, to the pi pulse, so basically. And when k goes to 1, so you have a very long control time, but you are also very robust. So basically, so by playing with this parameter k, so you can find a compromise, a balance between robustness and speed of a control process. Okay, so at the end, so if you don't have any problem, so with the control time, and if in your experiment you can consider so very long control duration, then so for sure, so you have to choose a k very close to 1. But if you have some relaxation effect that you want to avoid, then in this case it's better to take a small value of k. Okay, so it's
and for implementing the geometric phase,
yes,
it seems like you need to have large differences between the k trajectories.
yes.
Does this limit how much phase you can really accumulate?
Yes, exactly. So yes, so it's a point that we do not verify, but it's clear that so in this case, so since we have to consider two successive tennis racket effects, so the process is less robust. So we have to choose some specific values of k, and we need also so for some angles so we need a large difference between so the two ka and kb. So yes, you're right. Yes. But for the moment, it's only some numerical simulation, and so for us, it will be very interesting to focus on a specific example. To see and to understand how to adjust such parameters. So it's so this point is not so clear for the moment.
Still regarding the same type of pulse, is the cancellation of the dynamic phase collection included in the double tennis effect pulse, or is it something that needs to be accounted for on top?
Yeah, no. So we have to. So it's not so straightforward. So we have to adjust. So basically, so the control time of a two tennis racket effect to be sure that we cancel so the dynamical contribution of the phase of. So it's not so straightforward. So do you see so what I mean? So it's not so easy to explain so without so the equations, but so it's if you consider any so two tennis racket effect, so in general it does not work. So we have to work on we have to choose some specific parameters, and in particular so the control time for the two tennis racket effect to be sure that the dynamical contribution is 0. The total dynamical contribution is 0.
And would it be that in practice, so this means that you have the two conditions for a given phase, that of the shine you were showing,
Yes,
and
yes.
the extra condition or to
yes, yes.
And does that mean that you can't actually implement for any phase? You can't find a solution, or is there still a solution of two different Ks such that you satisfy both conditions?
So I'm not sure to understand so your point, but so we can implement so any so unitary gate. So with for instance the phase gate and with any phase.
Okay, that was the question.
No, it works in practice, yes. And even so, we have also some solutions. So for the Hadamard gate, so it's not restricted at all to a phase gate and to any 1 qubit gate.
And maybe now just a quick question about the dynamics we saw for an example. I think this was the implementation from the group of Stefan Glasler.
Mm-hmm.
So there you could see the M1, M2, and M3 all having dynamics, but my understanding was that you have to essentially put one of the inertias to infinity such that then one of these M's would be constant, or is this
No. So when we put, when we put one of the moments of inertia to infinity, so basically it's just that in the block equation, so we eliminate one of the three control fields.
Okay.
Okay, and that's all. So for instance, it means here that so we eliminate, for instance, omega-1 term, and we have only two control fields. Okay, and we just identify omega-3 with M3 divided by I3 and omega-2 by M2 divided by I2, and then we have so the expression for the control fields.
Okay, yeah.
Okay, and then you can make this the experiment, and that's all, and it works. No, and the good point is the fact we have the analytical expression for the control field, which is not so so common.
Thanks again.
Eugenio?
Yes, can you hear me?
Yes, sure.
Okay, thank you for the very interesting talk. I was wondering about what you mentioned at the end about the realization of probably experimental realization of the tennis racket effect on a real molecule.
Mm.
So is it this tennis racket effect? The realization should be induced like with a laser field, or how? What is your?
Yes, exactly. So it's with some laser field. So we have two problems. So to make. Yeah, sure. So we have so it's basically so in gaze phase. So we have a cell with so a gaze with the molecules. So for instance, the chlorobenzene or any asymmetric top molecule. And we use some specific laser fields, so some femtosecond laser fields. So basically, we will need so different polarization. So we think with my colleagues, with my experimental colleagues, so we think that we could use linear and circular polarizations for the laser fields in order to induce so the rotation around so the transverse axis. Okay. So it's not so trivial because so we have to induce so a rotation in a body fixed frame and not in the laboratory frame. And then so it's the first problem that we have. And the second problem is from the experimental point of view to be able to measure the final position of a molecule or of a tennis racket. So basically it means to be able to measure so the three Euler angles at the final time. Okay, because from a quantum point of view, so you cannot see so the molecule, and so we need some measures. And so it's possible. And in general, the idea is to send on the sample another laser. And so you are going to change so either the polarization of a laser, or so due to the position of a molecule, and so this so from this change, so you can deduce, for instance, of the final values of the Euler angles. Okay, but it's so this experiment is not straightforward at all, and it's very difficult to realize, I think.
Okay, no, because I was wondering about so can if it is doable also from a controllability point of view, because it's not clear if it is controlled. Like for example, it may depend on the position of the dipole inside the molecule.
Yes, exactly. And no, so you're right. So for the moment, I do not discuss at all so the dipole moment of a molecule or the polarizability tensor of a molecule.
Yeah.
And so you're right that it's so I think so one of the first point yes to be able so to because so the idea is so with so with a preparation with a laser field to go to a specific initial state. And so for sure, so first question is to be sure that for instance that the system is controllable. So with the dipole moment, for instance, of a molecule, to be sure that so we can reach this state. Yes, yes, okay. I agree with you.
Okay.
Yes, yes.
Okay.
But
Okay.
I know. So I know your work with Hugo. I think it's. Because you work on this problem with Hugo and no, it's yes, it's you. Yes, yes, sure, yes.
It is, and yeah, because I was working also with asymmetric top, and there are no controllable cases. So I was wondering about this, for example.
Yes. Yes. But the point is that from the experimental point of view, in general, so the experiments are very so difficult and complicated, and so we cannot reach a specific target state. So in general, it's maybe more a kind of a region of the Hilbert space, and even if we are not exactly controllable, so maybe it's not so important.
Yeah, maybe it's still doable.
Yes, it's still doable. Yes, it's a kind of
reachable set.
Yes.
Okay.
Yes, but from a fundamental point of view, so this question, this issue, I think it's very important because for the moment, for instance, in the PRL paper about the nanorotor, so they just make some numerical simulations where they assume that they start so from a given initial state. And they do not solve at all. So this question about so the controllability and how to prepare so the molecule or the nanorotor in this initial state. So it's so I think it's yes, this point is a key point so for this study. So you're right.
Okay. Thank you.
Yeah. So I think that's all. Okay.
So thank you very much, everybody, and yes. So do not hesitate so to contact me. So if you have any question or comment about so this work, so I will be very happy to discuss with you or to send you some references. Okay.
Okay. Thank you.
Okay. So
thank you very much.
Bye-bye.
Thank you.
Have a nice day.
Bye. Have a nice day.
Have a nice day.